it is possible to build a highly maneuvering unmanned fighter aircraft. It could be built with an X-wing design. That would enable it to turn in any direction without having to roll into the turn, so it can make the turns more quickly. It could have turning rates of perhaps as high as 15 Gs, as opposed to 9 Gs for a manned fighter aircraft. The air inlet would have to have airflow coming into it from any direction. It would probably look like something like the front end of a MiG-21. It would be a single-engined aircraft, and depending on the size of the engine, which would determine the weight of the aircraft, the distance from tip to tip of the wings could be 15 to over 20 feet. There is no good way to put landing gear on it, and the landing gear represents a weight. So removing the landing gear helps it to maneuver better. But you would need some kind of frame with wings which can pick up the aircraft and get it into the air for flight. For maneuverability, an aircraft wants a high net power to weight ratio. The net power is the thrust of the engines minus the aerodynamic drag, and the weight is the weight of the aircraft. In this design, there are some weight savings. Removing the landing gear will save several hundred pounds. In addition, for the weight of the wing per area, you can reduce the wingspan. It's not engaging in takeoffs and landings, therefore the wings can be designed for higher speed flight. You can reduce the aspect ratio of the wing, which is the wingspan divided by the chord. If you reduce the span of the wing, the bending moments at the root of the wing are reduced by the square. If you reduce the wingspan 2.7, you reduce the bending moment 2.5, and you can make the wings larger without any increment in weight. There are, however, 2 additional wings. You save weight on the landing gear, you save weight on the weight of the pilot, the ejection seat, the armor plate for the cockpit, the control panel, the life support systems for the pilot, the canopy, as well as the fact that removing the cockpit allows the fuselage to be made smaller, and that also represents some weight savings. Again, all of those weight savings have to be considered in the light you have 2 additional wings. The removal of the canopy reduces drag, but the extra set of wings means you have more wetted surface, and that is an increase in drag. If you assume that a fighter plane has a lift to drag ratio of 15 to 1, and the thrust is 100% of the weight, which depends on altitude, the thrust equal to the weight does include, of course, afterburner. The thrust required to fly in a straight and level line is about 7% of your total thrust. 93% is available for maneuvering. If the increased wing surface increases it by 3% to 10%, you've been reduced from 93% available thrust to 90%. That's about a 3% loss. Then you're dealing with the weight of the aircraft. If the aircraft is heavier, that's an additional reduction in net thrust to weight. It looks like the entire aircraft can be done, at least in an empty state, of about a 5% reduction in thrust to weight. That is some loss in your ability to restore power during maneuvers, also for climbing. So it looks like a manned fighter plane will be able to climb faster than this aircraft to some degree. But it doesn't really matter completely, because what matters is, can the unmanned aircraft get into a position to fire a missile at the manned aircraft? If it can outclimb and intercept the fighter plane, it does not matter how fast the unmanned aircraft climbs. If the wingspan is reduced and the root length increased, if the same what's called thickness to chord ratio is constant, which is the top to bottom height of the wing versus the front to back measurement of the wing, what happens is you have very large internal volumes in all 4 of those wings. That enables a very large carriage of fuel. That weight of fuel also reduces net thrust to weight, but it gives you long endurance. Because of the X-wing design, the wings are only 0.7 efficient in each direction. That's the cosine of 45 degrees. If the design point was for the planes to turn at 15 Gs, with a current plane designed to turn at 9 Gs, the wings would have to have 2.5 times the surface area. The X-wing aircraft would be controlled from an AWACS aircraft. It would have to be a larger version of an AWACS aircraft. In addition to the normal radar operators, they would have to have the pilots for the X-wing aircraft. There might be 40 pilots to control 40 aircraft. In addition, you might have 4 to 8 additional reserve pilots, so that the pilots could take a rest. You then have 40 aircraft operating away from the AWACS aircraft. At 40,000 feet, the horizon line, direct line of sight from the radar, is about 200 nautical miles. So if the AWACS aircraft was 100 miles and back of any kind of force boundary, the X-wing aircraft could operate over 100 miles past that boundary into hostile airspace. The X-wing fighters would have the capacity for in-air refueling, so they would fly back and be refueled. They would fly until they need maintenance, whatever the longest flight they can have without needing maintenance. If maintenance required every 100 hours, they could fly for 4 days. The AWACS aircraft would be transferred. The AWACS aircraft and their crews would switch over every 8 hours or so. And so the fighter aircraft would be handed over from one AWACS aircraft to another AWACS aircraft. For refueling, they would fly back, and they would then be under the control of the tanker aircraft. The X-wing aircraft would have 3 groups. There are the groups refueling, going back and forth from the area of operations, the X-wing aircraft that are actively engaged in operations, and then there would be a reserve group of additional X-wing aircraft. You might have 40 aircraft in the forward group and another 20 to 24 aircraft in the reserve group. The 40 aircraft are being actively controlled. The reserve group is basically flying around in circles under autonomous control. This is where learning systems come in. The pilots of the X-wing aircraft would be receiving the information from the AWACS aircraft. In addition, when they designate a target, the X-wing fighter would send them its onboard radar imaging as well as visual imaging. But that is the only information it would send. It would only send the information for one specific target. The goal is to limit information transfer to make it harder to jam the radios. For visual information, learning systems on board the aircraft, the X-wing fighter, artificial intelligence, would try to identify the aircraft being targeted, whether it's a single-engine aircraft, a twin-engine aircraft, and preferably actually the specific type of aircraft. It would then send that information in condensed form. It would have an identifier for the type of aircraft. It would not send the pixel-by-pixel transmission of the actual photograph of the aircraft. And then it would send information on the location, scaling numbers, and rotation numbers. So it would be recreated for the pilots on board the AWACS aircraft. When they engage a target, the X-wing aircraft would have an onboard attack plan. It would be overridden by the pilot in the AWACS aircraft. So whenever the AWACS aircraft tells it to do something, that is what it would do. It would then update its attack plan at each step. If communication links are broken between the AWACS aircraft and the X-wing fighter aircraft, the X-wing fighter aircraft would operate autonomously with its onboard attack plan. In the event of a large-scale confrontation, the reserve pilots, the 4 to 8 pilots who are rotating on and off, would be called to their workstations. They could fly at least an additional 4 to 8 aircraft. Planes from the reserve group would be assigned to those pilots. If an aircraft was damaged or ran out of missiles, one of the reserve aircraft would be assigned to the active pilot. So that pilot would continue in the fight. If there was a really serious confrontation, all of the reserve aircraft would be flown forward, and some of the pilots would be assigned to operate all of them. So if you have 8 reserve pilots, you have 24 reserve aircraft, each pilot would effectively be controlling 3 aircraft. They would fly forward, they would designate a target for the X-wing aircraft. The X-wing aircraft would make that attack autonomously. They would then move on to assigning an attack for another fighter plane and another fighter plane. And then they could engage in specifically flying one of the aircraft. The main advantage of the X-wing design is its ability to sidestep a missile. If a missile is coming towards it, it can make one very fast, very hard turn. It can turn faster than a fighter plane, and because it doesn't need to roll the aircraft to make the turn, it can achieve its peak turning rate much faster. That means that the X-wing aircraft has to have systems over the aircraft to identify missiles approaching from any direction. Because of its high turning rate, the X-wing aircraft can avoid both air-to-air and surface-to-air missiles. That enables it to function over hostile airspace and have a good chance of survivability, as long as its systems can see a missile coming. Another possible option is to give each of the active pilots 2 aircraft to fly, one aircraft which he is actively flying, and the other aircraft functioning as a wingman. Both aircraft would be designated to attack the same target. There is a high workload in flying an aircraft. so the pilot could not actively control the wing aircraft. It would have to work mostly autonomously. The pilot could give them simple instructions to fly on the right side of the lead aircraft, to fly on the left side, to fly close, to fly further away, to fly above, to fly below. That might be enough to give a tactical advantage in the two aircraft set in attacking an individual aircraft.